We are starting. All right, we have a quirky topic today. We have a quirky topic today, and we have a quirky setup. So let's get started. So I spoke with IT, and this monitor is bust. It's fried. So it's also really big, so they have to get facilities to come in and replace it. So until they do, they sort of wheel this in temporarily. So technology. So I've got my high-tech display and my really high-tech display over there real quick. So homework 7 was due today. We were talking about it a little bit before class. It seemed like everybody was okay with the big picture. Maybe there's those little things that you have to redo and whatnot, but by and large, seemed like everybody did pretty well, or we'll see on the grade on that. We are starting our last big topic in the class, and I meant what I said. It is actually a little quirky, and you'll understand what I mean, but what we're going to be talking about is the concept of an influence line, and specifically the means in which we construct an influence line is we use what's called the Mueller-Breslau principle. You will understand what that means here in a bit, but I kind of want to take some time off to the side and just talk about just what the heck an influence line even is, okay, and why we care. Okay, so up until now, we have only dealt with a structure and there's loads on it, okay? And if we take that structure and we change the position of the loads, or we take some loads off, put some loads on, if we change the loads by a little bit, it becomes an entirely different problem. We have to repeat the structural analysis from scratch. We would have to rerun the software analysis. It's just different, okay? Moving loads raises essentially 2 classes of questions for us as engineers, okay? Because I want to, again, everything that we do in here, I want to try and make sure that there is a connection to the real world, okay? So the first question is, can we develop a tool that can handle moving loads? And I think, honestly, we all probably understand why we would care, a bridge, right? Bridges are subjected to transient load events. There's the truck here, and then there's the truck here, okay? We've talked before about, in the land of truss analysis, how we can get some members that are zero force members, and one of the things I said was, because we had a question, why even have zero force members in a truss to begin with? One of the answers is the truss may be, or that member may be a zero force member when the loads are there, and if the loads move, maybe it doesn't become a zero force member. So that is a very real issue that we need to deal with. But the tool, just having the tool is fine. What are we going to use the tool for? Okay. So the second question is, can this tool help us figure out the worst case load placement? Okay. We are engineers. We are interested in worst case scenarios because that's what we want to design for. So if I have a bridge, can this tool help us determine where to put the load to get the worst case scenario, and what is that worst case scenario? Because that's what we can design for, okay? And we do have a name for that tool. We call it an influence line. And so I would like to discuss influence lines today. Now, what is an influence line? All right, I'm going to say something, okay? I'm going to say something very clearly. An influence line is not a shear diagram or a moment diagram, okay? I'm going to say that again. An influence line is not a shear diagram or a moment diagram. You know what? I'm going to say it a third time. An influence line is not a shear diagram or a moment diagram, but they're going to look like them. I'm just going to tell you, they are going to look a lot like shear diagram and moment diagrams, but they're not, okay? What an influence line is it's a diagram that's used to assess moving loads. The way that it works is you have to identify a point of interest on the structure, okay? So a point of interest could be something like a support reaction. So if I have a beam, I'm going to draw an influence line for that reaction, or that reaction over there, or that reaction. Your point of interest remains fixed, okay? Now your point of interest can also be internal response. So it could be the shears at a given point the moments at a given point, etc. So one of the, I guess, drawbacks to an influence line is that you can only draw influence lines at discrete locations along a span, okay? It is common practice in the world of bridge engineering to draw influence lines at every 10th point along the span. So if a bridge is 50 foot long, you will draw an influence line for every 5 feet, an influence line for the shears and moments at 5 feet, at 10 feet, at 15 feet, at 20 feet. And the idea is that that envelope of responses is enough to capture the maximum force. So when you start getting into the land of influence lines, you kind of see, yeah, after that, it's usually good enough. What we then do is we take a unit load, so there's our friend again, that unit load, that 1 kip load. We take that 1 kip load and we move it across the structure, okay? And as we move the unit load across the structure, we record the response for whatever point of interest that we're looking at. So, for example, if we're interested in the reaction right here, we take a unit load, move it across the structure, and as we move it, we record that response, that reaction there, and we plot it. And that resulting plot is the influence line, okay? Now, we are not actually going to use this definition outright a lot when we start getting into the land of doing these problems, but I do think you should remember this, because remembering this will be a gut check for what you end up plotting, and we're going to use that today. You'll see what I mean, okay? Now, in order to explain this, I would like to do a very basic example with you together to kind of explain what's going on, okay? So let's take a beam, okay? So here's a beam. It's simply supported, okay? And I'm going to take a single unit load and I'm going to move it across the structure, okay? And as we move it, I want to plot the influence line for the reaction at A, okay? So everybody follow along with me. Let me ask you this, okay? I'm going to borrow this marker right here because you're going to see it here on the slide here in a second. Okay, so here's the influence line. Call this AY. Okay, so help me out. If I put the load right smack dab in the middle of the beam, 1 kip in the middle of the beam, what are both of these reactions? Half a kip, right? So right here in the middle, that'd be a half. Okay? Let me ask you this. What if I took the load and moved it there? What is the reaction at A if the load is right here? 0. What about right here? What if I take the load and put it right over A? What is the reaction at A? 1. That is the influence line for the reaction at A. Pretty easy, right? See what I meant? I said these kind of look like shear diagrams and moment diagrams. They're not, okay? This is the influence line for the reaction at A, okay? This influence line, while incredibly simple, does a lot for us as engineers, okay? For example, okay, if I was designing this bridge and I was designing, let's say, the foundation of this bridge. Let's say I'm designing the foundation under this abutment. Where do I put my moving vehicle loads to generate the worst case response? Well, common sense tells me I stick them over here, right? But that's also what the influence line tells us. The larger values on the influence line correspond to the larger influence, okay? So if I wanted to maximize load on the reaction at A, stick all the loads closer to A. I'm getting that from common sense and from the influence line. Sometimes our structures are a little more complicated than this, and it's not that simple. We have to actually use the influence line to figure out where the load needs to go. Now, a couple things. This bullet right here, the distribution is linear, okay? When we're looking at statically determinate structures, influence lines are always linear. Every time. I cannot begin to tell you how important that statement is, okay? I cannot begin to tell you how many times I have been grading an exam and I give you an influence line problem and it's a determinate structure and I see these curved influence lines. No. Okay? If you are drawing a curved influence line for a statically determinate structure, you are doing something wrong. We can prove this later with the Mueller-Breslau principle. Okay? But you'll see what I mean here in a second. Now, let's make sure that we're clear. To test your understanding, this is the influence line for the reaction at A. What would the influence line for the reaction at B look like? It would flip it over, right? The influence line for the reaction at B would just go like that. Okay? Make sense? So far, so good? All right. Now, we need a process for constructing them. Because if I give you a really complicated structure, we could just move the load and compute the reactions every foot or so, and that would get to be a ginormous pain. Okay? But, again, let's keep some things in mind. Influence lines for statically determined structures are always linear. There is a reason they are called influence lines, because they're linear for determinate structures. Okay? Now, for indeterminate structures, again, if you have an indeterminate structure, they may be curved, they may be nonlinear, but that is only in the case of indeterminate structures, not for what we are dealing with. And I'll show you, I have some examples of this when we get to near the end of influence lines. I'll talk to you about what they look like for nonlinear structures. Now, more specifically, I want to talk about this. How do we prove it? How do we prove that influence lines are linear for statically determinate structures? And I guess more specifically, is there a way that we can develop some systematic process? Because if I gave you a structure, let's say I gave you a structure that looks like this. So there's a beam, let's say there's a support right here, there's a hinge, a roller, and a roller. Okay? So that's a statically determinate structure. But how do you determine the influence line for this? Am I literally going to expect you to move a load like every foot, and every time there's a load somewhere there, compute the reactions, move it, compute the reactions? That would be enormously difficult, right? That would take forever, right? I don't want you to do that. I want to develop a simpler way of drawing the influence lines for this structure, okay? I have a way, okay? The way is the Mueller-Breslau principle, okay? So let's talk about this Mueller-Breslau principle. This is our graphical means to construct an influence line. Now, the Mueller-Breslau principle is a mouthful, okay? But let me sort of skip ahead and show you what that is. Okay, so here's the Mueller-Breslau principle. This is what it says. It says that the deflected shape of a structure represents to some scale the influence line for a force effect if the quantity in question is moved through a small unit displacement. And I'll show you what I mean with my high-tech display here in a second. So I brought the hotness here. Let's see what I mean. All right. So basically, the Mueller-Breslau principle says that if you take a structure and deform it a certain way and look at that resulting deformed shape, that shape is the influence line. Okay? All right? So how does it work? Okay? Here's how it works. So the first thing you need to do is you need to identify your response that you're looking for. Is it a reaction? Is it a moment at a particular point? Is it a shear at a particular point? Whatever that reaction is, okay? What you then need to do is take that structure and remove from the structure the ability to resist that. So, like for example, if I was looking at this beam right here, okay, let's say I was trying to draw an influence line for that reaction, okay? What I do is I have the structure, I take the structure, and I remove that roller, okay? Now let's conceptualize this a little bit, okay? This structure is statically determinate. If I remove the roller, what does it become? Somebody said it, I heard it. What does it mean for static determinacy? Static determinacy is I equals 0. If I remove a roller, that becomes -1. And if I have an IE of -1, what does that mean? It's unstable, okay? So now I've developed an unstable structure. I then take this point and I move it through a unit displacement, a unit deformation, okay? So a unit deformation, if I look at this structure, why is it unstable? It's unstable because there's a hinge right here. If I were to take this point and pick it up, this structure would remain flat and all it would do is lift up like that. The influence line for this structure for that reaction is just that. That's the influence line, okay? That's what it looks like. And I'll show you some further examples of that here in a bit. But that resulting displaced shape is the influence line. Okay? Now let me show you something. Let me show you how this works. Now let's take a look here at this. All right. I have the influence, I have a structure here. Now let's take a look at the structure. It's two-span structure, but I have a hinge between these two spans. Now let's look at my little display here. I have a two-span structure and I got a hinge right here. Okay? Watch this. Let's draw the influence line for the reaction at A. So what I'm going to do is I'm going to remove from the structure the ability to resist the reaction at A. And then I'm going to take that and move it through a unit displacement. Do you see what happened? So watch this. So here's the structure. I move it through a unit displacement. See how this went up and that went down? See that? Let's take a look at this. Look what happened. So take this, move it through a unit displacement. By golly gosh gee, that's the influence line for the reaction at A. Because that's what I'm doing, okay? So like for example, let's take this. Let's take the reaction at B. So here's my structure. I'm going to remove from the structure the ability to resist the reaction at B. So I removed it out from there. So you can see it's unstable. And I take it and I move it through a unit displacement. Look what happens. So I move that through a unit displacement. You can see the shape. Notice that if from here to here is 1, then from here to here is higher than 1. See how it goes up?
How do you know which direction to move it?
You move it up.
Always move it up.
Well, for reactions, you move it up because
they're
a positive reaction goes up, yes. And that's a very loaded question for internal shears and moments. We're going to talk about that next time. Trust me. Now, what about this reaction over here, right? So, remove from the structure the ability to resist that reaction. But look, it's unstable, right? That's what I mean by unstable. If I take that point, lift it up 1, that's what we get. You get some really interesting findings with influence lines. For example, if you have this structure and you put a ton of load from here to here, that reaction is 0. Did you know that? Because if I put load in this part of the structure, it does not affect the reaction at C. That's what the influence line tells us. That if you want to affect the influence, or if you want to affect the reaction at C, only put load on this end of the span. That's what the influence line tells us. All right. A couple things. Let's follow this through a little bit more closely with the math. Okay. Influence lines, and let's look at some patterns here. Let's look at this. Okay, point 1. Influence lines always equal 1 at the reaction of interest and 0 at other reactions when you're talking about influence lines for reactions. This is not true, by the way, for influence lines for shear and for moment. Everything on this slide is just for when we're drawing influence lines for reactions. But look what happens. Like if I'm drawing the influence line for the reaction at A, I get 1 at A, 0 everywhere else. Look at B. 1 at B, 0 at the other reactions. Look at C. 1 at C, 0 at the other reactions. Because if I put the load directly over the reaction, I get 1 there and 0 everywhere else. Make sense? Influence lines are linear, right? My little display kind of proved that, right? So if I know that this is 1 and this is 0 and this is a line, 1 is to 12 as something is to 6, I can figure out that negative 0.5 by just using like slip ratios, just using lines, right? And look what happens for every influence line at the hinge. The hinge changed the direction. You want something else that's kind of cool? Watch this. Let's go vertical. What is that plus that plus that? This number plus this number plus this number. What is this number plus this number plus this number? what is that number plus that number plus that number? That plus that plus that. 1, right? The reason why is because the sum of the forces in the vertical direction must be 0 every time. You are placing a downward load. So all the reactions have to add up to be 1, right? Every time. So there's a lot of gut checks for what you're doing and whether or not what you're doing is correct. Does that make sense? Sound good? Okay, now I want to explain this example, but before y'all start drawing, just bear with me. I have influence line example 1A, and then I have influence line example 2A. What we're going to do is today we are only going to worry about the reactions. Then next lecture we're going to come back and we're going to say, well, what does the influence line for shear look like? What does the influence line for moment look like? So we're going to come back to these later, okay? So let's go to our notes here. All right, now I did some work here to kind of set this up. So let's see what we got here, okay? And if you need to scooch around to see this bizarre screen setup, I understand. Because, yeah. Okay. So today, all we're going to do is we're going to focus on the influence line for AY and the influence line for CY. Okay? That's all we're going to focus on today for this example. So let's do AY first. Now I want to make a point crystallized in your brain right now. How many solid length segments, how many solid rigid segments does this beam consist of? It's just one, right? It's not like this beam. This beam has 1, 2, right? So this beam, the influence line should only be one solid rigid segment, okay? One line, okay? Now, help me out. How does an influence line work? Let's go back to the Mueller-Breslau principle. We're drawing the influence line for the reaction at A. We remove from the structure the ability to resist the reaction at A. If that pin support is gone, and all I'm left with is a beam and that little roller, we got kind of like a seesaw going on, right? Kind of like a seesaw. And so if I take point A and lift it up 1, the influence line for the reaction at A looks kind of like that. Would that make sense? That is the influence line for the reaction at A. Before we move on, I want to take a step back and see, does this make any sense? Okay. What's this value right here? What about that value? Okay. Simple. So, this is 1. This is 0. How would we find that value? This value right here. Slope ratio. So can anybody eyeball that and tell me what this value is going to be? 1/3. Right? Because we go from 1 is to 30 as something is to 10. Right? So we can say, I don't know, you can call this whatever you want. You can call it HB. You can say, note H sub B is 1/3. So If that's 1/3, what is that? Negative 1/3. Okay. All right. Let's think about this. How many reactions does vertical reactions does this beam have? How many? I don't know who that is. Just gonna have to call them back. Sorry. My apologies. 2 vertical reactions, right? 2 vertical reactions, and the sum of those reactions must be what? Well, the sum of the forces must be 0, but if we're always applying a downward load, then the reactions have to add up to be 1. Does that make sense? So before we draw anything, what does the value need to be right there?
0.
What about right there?
2/3. 1.
And
1 1/3.
1 1/3 or 4/3, right? So that means our influence line needs to go like that. Does that comport with the Mueller-Breslau principle? Well, remove from the structure the ability to resist that roller. Okay? What does the structure look like if we remove that roller? It looks like this, right? Here's the beam, and there's a reaction right there. No roller, right? And if I take this point and lift it up one, what does it look like? It looks like that, right? So the influence line for the reaction at C looks like that. I can do better than that. Let's see if I can. I'm going to get this. No, I'm not. Technology. We're going to do this. Going to do that. Then we're going to do that. There we go. That's better. All right. Now we have our influence line for the reaction at C. That value is 0. That value is 2/3. That value is 1. That value 4/3. Now, again, if you do not believe in all this gobbledygook regarding, removing rollers and drawing lines, consider the load at D. So here's the structure. We have a roller here, a hinge there, a roller there. This dimension is 30 foot. This dimension is 10 foot. Now what happens if I place a load right here? Let's say I place a unit load right there. What are my reactions? Okay, let's sum moments at A and see what we get. Okay, so this is A, this is C. So if I sum moments at A, so what do I have? I have 1 times 40. That has to be resisted by some reaction here. CY. That's 30 feet from A. So 40 is CY times 30. So what does that mean? CY 4/3. And if I sum forces in the y direction, I have that going down. I have 4/3 going up. I need something else going down, right? I need AY has got to go down because I've got 4/3 equals 1.0 plus AY. AY is 1/3 going down. That one's going up. So AY is 1/3 going down equals 4/3 going up. That's exactly what we got on the influence line. Exactly. When we put the load here, AY is negative 1/3, CY is positive 4/3. Exactly. But that's the cool thing. The influence line is telling you the reactions when the load is anywhere. Now we're going to get into specifics of applications a little bit later. But if you want a simple way of explaining it, let me ask you a question. Would you agree that this diagram is telling you the reaction, let's say at CY, when a 1 kip load is anywhere, right? How would I use this diagram if I had a 20 kip load? What about a 57 kip load? So now I can tell you the reaction of any load anywhere.
Why don't we do this to start with?
We're getting there. You have to walk before you can run. Smart. I heard that. But we'll get there. Trust me. You're going to see some really cool stuff here with this. Does this make sense? All right. Now I'm going to confuse you. Let's look at this one. This one's different. Ooh. Now I'm making it interesting. Okay. So now I have a beam. Now look at this. We've got two 20-foot spans. This is 20 feet, that's 20 feet. Hinge, roller, roller. But we got a hinge right there, an internal hinge right there. So the structure, is it statically determinate, yes or no? What's IE for this structure? 0. Because we've got 1, 2, 3, 4 reactions, 3 equations of equilibrium, 1 equation of condition. Statically determined. Sorry, hold on. Cords everywhere. Let's make this bigger. And let's see if I can take this and move that up a little bit. Move that one up just a tad. I want to make sure I got room to sort of see the whole picture.
Okay.
All right. So we've got 3 influence lines that we're going to need to draw. Again, today we are only talking about reactions. AY, BY, CY. So, let's take it alphabetically. Start with A. I'm taking my time with this lecture because, again, it's quirky. All right? We remove from the structure the ability to resist the reaction at A. So if I have this reaction at A and I pull a this is Sparta and I just kick it out, okay? What does the beam look like? Okay? It's a beam, it's got this segment, and then there's this hinge right here. So what does the beam do with this roller or this support gone? What does it do? But what falls down? Just this part right here, right? It's just, it just falls down. Like this is an elbow, and you kick. I could have been that. There's this little tray here, right? Elbow here, kick the roller, and it just does that, right? So then if I take that point A, because I'm drawing the influence line for the reaction at A, if I take that point and I move it through a unit displacement, what does the structure look like? Let me ask, before we answer that, how many rigid segments are in this beam? 2. So all the influence lines should be comprised of just 2 lines, right? So if I take this point and pick it up, what does the structure look like? Can anybody tell me?
It just goes from up 1 at A to 0 at the hinge, right? And
Okay, what does this look like?
stays 0, right?
0. Nothing. It's exactly right. That's 100% right. So the influence line for the reaction at A looks like this. Where this is 1.0, that is 0, and if you want, you are more than welcome to label all these as zeros as well. But it's really cool stuff. It tells you that if you place a vertical load, if I stand on this beam anywhere from this hinge over here, it doesn't affect A for a hill of beams. It doesn't affect A at all. That's your influence line for the reaction at A. Does that make sense? All right, so let's do BY. Okay? Now, before we do BY, let's have some common sense about some things. The influence line for the reaction at B, what's the value right here? At this line. 0. What's the value right here? What's the value right here? Okay, so I know that this is 0. I know this is 0, and we'll say that is 1. So before we draw anything, we should have that figured out. Now, I remove from the structure the ability to resist the reaction at B, okay? Just like this. So just kind of like this. I remove from the structure the ability to resist the reaction at B. Let me stick that one back in there. And if I remove that, it's just sort of flops down, right? I take point B and I lift it up some, and I get something that kind of looks like this, right? This is 1, but that's higher, right? That part's higher. So the influence line is going to look something like this. That's the influence line. Now, we got some points to figure out. All right. And so we'll call this H sub hinge. We'll call this H sub 1. Bless you. Let's start off with H sub 1. Can anybody tell me how we can find H sub 1? Well, what do we know about this line? What is the slope of this line? How much do we rise up versus how much do we run? Is there something we can identify?
1 over
Rise up 1 over how much? 20,
20.
right? So I would say that 1 over 20 is H1 over what? 6. You see that? Because over that far end, right? Because what we're talking about, oh, that's messy. Right? Because this is 1.0, this is 20, and we're trying to figure out h sub 1, and that distance is 6, right? So therefore, if I wanted to solve for h1, I multiply both sides by 6. H sub 1 is 6 over 20. And 6 over 20 is 3 over 10, or 0.3. Does that make sense? So, let's see how you all are at your mental math or physical math. You got pencils or electronic pens. If this is 0.3 and this is 1, what's that? What's that? 7/5. That's exactly right. 1.4. That's 100% right. Because 1 is to 20, right? As something is to 28. So 28 over 20. 28 over 20, 1.4. 100% right. So this is 1.4. Boom! Influence line for the reaction at B. Done. I told you this was quirky. It is quirky, isn't it? All right. Now, does anybody have any questions? I don't want to just steamroll through this. I want this to be understood. Everybody good? Okay. All right. Now let's see if we can tackle the influence line for the reaction at C. What's the value right here? 0. What does the value have to be right here? Negative 0.4. Does everybody see that? So let's just sort of write these down here. Let's just sort of sketch these down. Okay, so this one's got to be 0. This one's got to be negative 0.4. What about right here on the B support? What's the value need to be right there? 0, because if the load is directly here, if the load's here, there is no reaction at C, right? So that's got to be 0. This is 0. What about over here at the section cut? What's it got to be? I'm just labeling it down here just before I start drawing it. 0.7. And this one's got to be 1, right? So, I didn't want to do all my labels before I actually draw it. So I just sort of lifted them down there. Okay. Just like with this. 2 solid pieces. I remove from the structure the ability to resist the reaction at C. Lift that up. And what do we have? Pivots around this, changes direction at the hinge. We go down, back up. The influence line for the reaction at C looks like this. And then shape. 0.4, 0.7, 1.4. So now I can erase that, erase that. So you get some really interesting dilemmas. So like, let's look at the beam. If I want to get the worst case reaction at B and I have a single load, where do I put it? If I'm designing B, like if I'm walking across the beam, where would I be standing to get the worst case effect on B? The hinge, right? Because if I stand right over B, I'm generating 100% of the reaction. But if I move away from B and stand on that hinge, that's an even worse effect on that supported B. It also tells me that if I stand on the hinge, I got some uplift issues at C to worry about, right? Because C's got to hold down, right? So the influence line tells me that I better design C so that it can handle some uplift, right? B's probably going to be my worst case design in terms of just sheer amount of load, right? And with support A, as long as there's no load over here, I got nothing to worry about, you know? It's kind of crazy stuff, isn't it?
Why did you cut that section?
We haven't yet.
Why do? I know, but
So you're talking about this section?
yeah, why is that? Why is that a point of interest? And how do you know?
I will explain.
I'm sure it's for the moment.
Yes. So Monday we're going to draw the shear and moment there,
Okay.
the influence line for the shear and moment there.
Is there like a? I'm sure we'll talk about it.
Is there a reason why I picked that point?
like at 6 feet?
No, not really. I just picked something. I'm dead serious. But let me say this. So in the land of bridges, it is conventional to cut every 10th point. So if a span is 20 foot long, it's typical that you cut at 2, 4, 6, 8, 10, 12, you know, and all the way across the span. So 10th point, because you can only evaluate shear and moments at discrete locations, so you need enough of them to be accurate, but the more that you do, you start getting to a point where accuracy doesn't matter. So 10 points is conventionally considered like what you need to do. Did this make sense? It's weird, isn't it?
It is quirky indeed.
What I told you it was quirky. All right, what we're going to do next time is, now before you leave, I want you to pay attention to this, all right? What we're gonna do next time is evaluate influence lines for internal response, internal shears and moments. And the rules are gonna be different. So here's an example. If you are drawing the influence line for the internal shear and moment right here, here, and here, it's 0. Because if I put the load directly at B, there is no internal response in the beam. It's just all going to B, right? So the rules change. So you got to be cognizant of what you're doing and pay attention to what you're drawing and why you're drawing it, okay? And the rules that we use for shear and moment are even quirkier. So I really want you to get comfortable with this. I have a homework assignment that all we're doing is influence lines for reactions. So in a weird way, it's the fastest homework probably this entire semester. Just draw out some lines and submit. But it also might take you longer than you think because you got to sit there and think about it. So he's laughing. That's all. All right, that's all I got, everybody. I'll see y'all on Monday. Y'all have a wonderful weekend.